are listening to Neurosalience, the OHBM podcast.
Welcome to the Organization for Human Brain Mapping Neurosalience podcast. I'm your host, Peter Bannattini. Here I interview brain scientists and discuss their work as well as the latest advancements and challenges in the field of brain mapping. Today's guest is Dr. Pedro Valdes-Sosa, who's the General Vice Director for Research of the Cuban Neurosciences Center, which he co-founded in 1990. He studied medicine at the University of Havana and graduated in 1972. He's also studied mathematics in 1973. He obtained his Ph.D. in 1978. In 1979, he did a postdoc on neurometrics and computational techniques and biophysical modeling of brain electrical activity with Professor Roy John at the Brain Research Lab of New York University. He's also a full member of the Cuban Academy of Sciences and the Latin American Academy of Sciences. He's also associate member of the International Center for Theoretical Physics. He's been invited professor of the Institute of Statistical Mathematics in Japan, invited researcher of the Brain Science Institute at Riken, Japan, and honorary professor at UCL. So Pedro is known not only for his innovation and rigor in EEG analysis, as well as analysis in other brain imaging techniques, but also for his highly collaborative work and passion to improve science development, communication, and dissemination in less developed countries. He's currently flying back and forth between Havana and Chengdu, China, where he's developing pooled databases for quantitative EEG. And in this conversation, we cover his history, some of his important mentors, some of the things he's passionate about. We delve into a few of his papers, of his many papers, talking about extracting novel information from EEG and sort of revealing that there's still a lot we really don't understand about the EEG frequencies, about the signal in general, and there's still a lot of work to be done as far as source localization for EEG. And we talk a little bit about the use of a pooled database for EEG and many other things. So I hope you enjoy the conversation. All right, Pedro Valdes-Sosa, thanks for visiting. It's great to see you. It's almost exactly 7 years to the month that I had the honor of being invited for a workshop in Cuba, and I was impressed, and it was a wonderful exchange. And and I've been realizing that just by looking at your work, you've been extremely active in many things. And your expertise is mathematics and EEG, among other things. And we could just get started with your background. So thanks for coming. Thanks for virtually coming onto this podcast. I don't think many people know that you were actually born in the States. You were born in Chicago. So maybe starting there, maybe trace your background a little bit in terms of when you moved to Cuba and where you had your education and collaborators and mentors and things like that.
So actually, I was born in 1950 in Chicago at the Norwegian American Hospital. My father was an intern who then did his residency in Chicago. My mother was an English teacher, and they went there in the late 40s. So I grew up visiting Cuba, being in Chicago. The house was very, let's say, oriented towards science and rationality. I got interested, for example, my dad and my mom, we would study classics. They bought me a chemistry kit, the usual thing. I have a twin brother, and we would, part of our time would be spent looking through, small microscopes and stuff like that. But one thing that really marked me was that my dad loved Scientific American, the Scientific American of the 50s, which was a bit more expanded. And one of the things I read when I was, I'd say about 11, was a paper by Walter and Imitation of Life. And it sort of described using circuits to model parts of the brain. And you know what? At that time, I forgot about it later, but I said, I'm going to go into this field of engineering, mathematics, modeling. I was very young. So my family moved back to Cuba in 1961. I actually jumped a few grades now. And me and my brother, there was this plan to train medical doctors. So I got into the medical school when I was 16. And when I started studying medicine, these things I've read about using mathematics, electronics, what was called cybernetics at that time, it captured still had my attention. And when I started studying medicine, I got really interested in the generation of the nerve impulse. We're talking about 1966, 1967, no? And I started reading the classics, no? All the papers on the generation of the nerve impulse, and I realized that my math wasn't that good. So what I started doing was kept on studying medicine, started studying math on the side, while I read papers, and then I was very lucky because in 1969, I met before 1968, I met one of my mentors, but then I met my other mentor in 1969. Now, they're Thalia Harmony, who is from Mexico, but went to Cuba to help develop science. And it was Erwin Roy John, who, he spent his last years working at NYU at the Brain Research Labs, which he headed. And so I was already interested in math. I was studying math. And then I met up with him, and Roy and Thalia were very interested in the use of computer techniques to study electrical activity of the brain. And the reason was very simple. They thought it could unlock cognition. It could unlock, for example, Roy John was one of the authors of the P300 paper. And I remember my first discussions with him were on factor analysis and whether that could bring out the states of the brain. We're talking 1970. I did factor analysis on a very old-fashioned computer by programming in machine language the Jacobi algorithm to extract eigenvectors and eigenvalues. So this tells you that I had a very atypical medical. It's more typical now. I've seen a lot of my friends, like Michael Breakspear. A lot of people have gone into both fields. No?
Yeah.
But it's been very frequent. So what happened at that time that we started discussing these things is that Roy John got a donation from scientists of New York for a special purpose computer. The only thing it would do is to extract average evoked potentials. And this he donated to the center where Thalia and where I was a young student, no? And there I started using the special purpose computer. But then a year later, a group of my friends developed in 1970 a Cuban computer, which was essentially equivalent to the PDP, which is what people used at that time.
Yes.
It wasn't copied. It was, let's say, designed. It was, how do you call it? When you know how it works, and then you engineer it backwards and get it together.
Yeah.
Back engineered. So we knew that this was one of the coolest computers. We couldn't get it because of trade embargoes and things like that. So these guys in 10 months, they constructed the computer. That's where I honed my programming skills, and I did all this other stuff.
And the programming was all machine language programming?
It went through 3 generations. So the first was machine language, hexadecimal. The memory was so short that you had to first fit in the compiler, run the code through, and then fill in. Then you ran in the operating system. We're talking about 4K of memory. Okay, 4K of memory to do everything.
Wow.
So that was interesting because that made all the group be very keen on optimizing code. Okay, and that's a habit that one keeps. Now we're spoiled. We get giga and petabytes, no? But Anyway, what happened then, I decided with my mentors. So Roy John was very active in mechanisms of memory. He was one of the authors on the P300 paper. He described endogenous evoked potentials in the late 50s in cats. So, but he was also very interested in the use of this in clinical applications. And this was more or less the same things that I've continued doing. So we got our computers going in Cuba. He had his computers going, and we were collecting data, and we started developing methods for extracting, let's say, biomarkers from event-related potentials in EEG. And then we, at that time, what was very popular for this sort of thing was traditional classical multivariate statistics. We didn't have deep learning, but we did have discriminant analysis. Yep. In fact, in 1969, I did one of my first published paper is a cluster analysis of the shape of evoked potentials in healthy subjects. Okay, and this did a lot of this. That was so I programmed an algorithm that's still used. It's called the Wishart algorithm. That just it's an agglomerative method to combine and the shapes of evoked potentials. There's a funny part there. Well, my twin brother, it was one of the sample because we started differently. I was more interested in math, physics. We both studied medicine. But then he was more interested in surgery, experiments, and things like that. But we ended up at the same lab. So he was one of the experimental subjects, but he fell asleep. So suddenly there's this cluster of one guy, totally different, and it was my brother, my twin brother, who simply was, on his own as an outlier because he had fallen asleep. So, so that shows that even at that time, we were starting to look at this possibility. So what came out of a long collaboration, which is really remarkable because it occurred during a period where there was a lot of political tension between the US and Cuba. Nevertheless, there was never an interruption of scientific activity, trying to do things for the benefit of people, for knowledge. And this led up to the idea that one could use numerical methods. I'm talking about cluster analysis, discriminant analysis, to try and factor analysis, of course, which is something we used a lot, to chart out what would be the space of normal development and then look for deviations of this. And that generated a joint paper between the Cuban and New York group headed by, the paper was, the first author is Roy John in Science. Yes. In May 1977. If you consider that EEG is also a sort of imaging modality that at that time was only on the scalp, but then later we started with source analysis later on. That was one of the first things because the EEG was accessible. At the time we published that, there was no MRI. Okay, we're talking about 1977. It's the work of the previous 8 years. What we have now is much larger samples, better defined. Not categories like in DSM. No, we have a better. We have the phenotyping much better, and of course the machine learning methods are much better. But the questions, I think, are there. They're the same question.
They're pretty much the same. And how many leads did your EEG have at that time? Like, was it?
At that time, what was standard was to have from 90 to 25 leads alone, 1 minute of EEG, resting state EEG, and then event-related potentials. But this allowed us not, we didn't say we were going to do very precise source localization. You can do some. As you have less leads, your full width at halfbacks increases for any of the source imaging methods. So we were clear that we were not going to get very precise, let's say, topographic information, but detection of state is something we did get. In fact, from that work, one of the normal samples we included was already a multinational work, was data from the island of Barbados. And why is this interesting? Because this was a time after they separated from the UK, became part of the Commonwealth as a separate. They had a situation with malnutrition, what happened at that time is that they solved the problem. The government solved the problem. And the people who were engaged in solving the problem invited Roy John to do a study of EEG of children with malnutrition and that didn't have malnutrition.
Wow. Okay.
Now, that study, these people who had malnutrition and didn't, were followed up till the day today. They're still, it's a 50-something-year-old study.
Wow.
So we went back with this 19-lead EEG, which is what was available at the time. Actually, the system was totally equivalent to ours because our engineers were in contact. So we went in, and 45 years later, we did the EEG of a number of these people.
Wow.
And let's say the fingerprint, the change that malnutrition produces only in the first year of life, even if you solve it afterwards, lasts all life.
Wow.
This is interesting.
That's really amazing. So there's a signature. So what was different? Like what was the signature that was different, and what do you think caused it?
Slow wave activity, excess of beta activity. And we have a paper that's now under review in Neuroimage that has the 45-year-old study. Okay.
Wow. And
we have the description there. We have now the modern discriminant equations. But our point that this illustrates something, and it is that the EEG used appropriately can give information that is easily deployable, low cost, and can be integrated. That's our idea, into health systems and put at the service of underserved populations, all over the world. So that's how this started at that time. What happened afterwards? Well, I went to NYU. I did my postdoc in NYU 1979, 1980, where we continued working on this sort of thing. I was engaged there not only in developing the methodology, the multivariate statistics, the EEG frequency analysis, but also in working with micro computers. So the Apple came out, and I remember that a few days after they started selling it, I was walking with Roy John down the street, and we see an Apple, and we look at each other and said, "This is what we're going to use." So we went in, we bought one, and the NYU engineer, we rigged up an A to D converter, we hooked a small system of EEG, and in a month we had an EEG system running.
Wow.
With an Apple computer. And what I programmed that was used for 5 years at Bellevue in the coma center was a coma monitoring unit. That was my project as a postdoc. And so we used it multivariate statistics, and we would see with continuous EEG using needles, we would see the brain state, which we obtained multivariately, and then have what we called self-norms, and then how people would deviate. So these are all topics that have been taken up much better by other people, looking at consciousness, whatever. But it also helped us fix the technology.
Yes.
So in the 80s, when I returned after my postdoc, what we did was to redesign our system, which was based on a mini computer to a microcomputer, and started introducing it into the health system. And there we found some interesting things, that not necessarily what scientists think is useful is what clinicians think that's useful.
Yes.
So there was a year or two of meshing when finally we said, okay, you guys do the specs and then do the quality control. And in the discussion, we convinced them of things. And we set up a network in the country. And the first thing we tackled, because we said, okay, and this is a question that comes up again in discussions in different countries when we want to launch brain initiatives, especially in lower middle income countries. We said we have to look for an example where we can solve a problem that can't be solved easily any other way and will convince the decision makers. In our case, everything is funded by the government. So the government, in this case, that it's worthwhile, and the medical profession. So what we picked was to try to detect hearing loss. And this was Mitchell, my twin brother's decision. He's very acute at picking out the important problems. He said, let's try to do a screening of hearing loss of newborn babies.
Huh.
The point is that we developed using this microcomputer, a technique to detect the presence of auditory evoked responses. And then what we did was to implement screening of the Cuban population of kids.
Yes.
Because the idea that's been behind a lot of our Cuban science is preventive medicine. That is to say, not to put the resources only, let's say, at the highest level of hospitals, but also to look for technology and methods, and then create a system that can be used to do screening, let's say, in a more massive way. So what we set up was a hearing screening program with the Ministry of Public Health, which took children at risk. And we're now pushing it, but the pandemic has slowed down things. We've been pushing towards universal screening, which is what we think has to be done, which is every child that is born should be screened for a certain number of things. But at that time, what was economic was something we learned from the health system in the UK. They were doing what they called, they were doing a two-stage screening. They were taking children at high risk and then examining them. So in several stages, and that we learned something, that you can use something that is very widespread, let's say massively, then it's like a screening process in a pyramid. Then you can put more and more technology, and that's very cost efficient.
Yeah.
This is the type of science that we've been doing and engaged with other people too. So that was something that got us interested in public health. So I was interested not only in the math, the methods and things like that, but I was also interested in the application of this. Without saying that, I also was interested in doing experiments and developing methods. And the first direction this took is that we decided that we had to go to source analysis. And our Dietrich Lehmann, these are names now of people that are no longer there. In fact, I have to tell you that in 1990, we had a beautiful meeting in Cuba, which was called, there's a book out there called Machinery of the Mind.
Yeah, heard of it, yeah.
And then we had Dietrich Lehmann, we had people like Pribram, we had the main people there at a symposium on how to understand the mind and how to use that mind. So that book is around there. Now, so Cuba had become, together with New York and Switzerland, there was a lot of going back and forth of ideas.
Yes.
And one of the ideas was doing source analysis. So our group started working as usual with dipoles, and then we sort of moved towards multiple dipoles, and then we went into distributed solutions. In fact, there's a whole school of people who have been producing inverse solutions that came from training in the Cuban Neurosciences Center. People have heard a lot about Loretta, things like that. These people were trained they got their Ph.D.s in the Cuban Neurosciences Center.
So just to jump in really quickly here, I mean, you talk about like for screening, for instance, I mean, and that's potentially, extremely useful for many different things, and sort of like, right, you can look at trajectories but the main thing was hearing loss, I guess, and and there were potentially other things as well. But also regarding source analysis, before you go into that, you might want to talk about just before you go into some of the issues of source analysis. I've always felt like, MEG is easier for source analysis because you don't have to worry about the conductivity differences of the skull and the scalp. And so is that able to be overcome?
Yes, I think so. Let me tell you first, it depends on the number of sensors. Already in 1987, at one of the first MEG conferences, Roberto Pascual and Rolando Vizcay, they're two of my PhD students now. Rolando Pascual is the guy behind all the versions of Loretta, and Rolando Vizcay is a brilliant mathematician. And they did a study that we presented at the MEG conference on the, let's say, the sensitivity of source analysis, depending on the type of electrodes you use and sensors. And we found that you could always, first, when you have more sensors of one kind than the other, it has a better full width at half max. It doesn't matter. If you have enough EEG, you can overcome a few MEGs. Second, we saw that if you combine EEG and MEG together, which is difficult technically, the problem that is very difficult with, let's say, the traditional run-of-the-mill MEG systems because of the way it's recorded. Now with the optically pumped systems, many people have started to envisage joint EEG, MEG systems. You're looking at different parts of the fields that are produced by the primary currents of the brain. So the theory says, and all these measurements say that yes, you can get improvement, but EEG has been, let's say, a bit beaten about. There's a paper we have in Neuroimage. It's called Bayesian model average, and that's instructive because we compare EEG, MEG with different methods, and we find that it's about 25 for 19 electrodes. 25 millimeters is the full width at half max. That's not to throw the thing out, okay? And there's a point where it asymptotes, okay? So with EEG, there's been a trend, and it's important to have more electrodes, but that makes it difficult technologically on the one hand, and second, there's diminishing returns. After you have about, let's say, maybe 50 electrodes, then you get a lot of unusable electrodes and so forth. So first, I think that the EEG needs better recording, active electrodes. It has to use dry electrodes, and I still think there's a lot to do there. I think that optical pumped magnetometers are also a new player in the game, but it's all electrophysiology. I mean, you're going to have to solve the inverse problem, and then I've seen how over the years the initial wild estimates of source localization have become converging, and you get more and more similar results. We don't have enough. Since I'm saying this, one of the difficulties for source analysis is there's not much gold truth in the there's not. We were able to analyze with now Takafuji from Ricket this preparation. I think you remember where we have 128 electrocorticogram electrodes, and we have the 1020 system, and then we can look at so there's a sort of ground truth here, but there's not enough experiments because the people that do let's say the laminar recording, the people that do the intracranial recording, they're focused on certain areas, of course, while the EEG and the MEG are, their field of view is large. So there's a contradiction here between what drives the studies, let's say, of electrophysiology in vivo in preparations and in experimental preparations and the clinical work. And then the other stuff goes with epilepsy, which is a very special circumstance. Fortunately, there are databases now available of joint EEG, electrocorticogram, of different types of recording. But I'm optimistic about this. The methods are improving. The convergence between them is greater and greater. And the technology is improving. Much faster, I have to say, for the MEG than for the EEG. We're still stuck, more or less, I'd say, for 10 years at the same level of technological development. But the MEG is really pulled ahead very well.
Well, and it seems that with EEG, if you could, make it seems like it's very easy to make now a very precise model of each person's head, and you can get a little bit further that way. But I actually have, I've always had sort of this question of, is doing source analysis even the right, you're assuming that there's these dipole sources. Is it, what if, there's two questions I usually have with regard to EEG. And one is, what if the source is sort of distributed among some complicated geometry, and how does that manifest? And the other one is having the connection, with EEG, you're looking at, oscillations, and it seems that how do you bridge the gap between spiking in specific areas versus, oscillatory? I guess that's one of the big questions in terms of what do these oscillations actually mean, and how are they produced, from spiking in that regard?
Let me start from the last question. The relation of spiking and slow potentials, that's a common problem, not for EEG and MEG, but also for fMRI.
Yeah.
Ever since the work of Nikos, looking at what part, of the intracranial recording in monkeys is related to the fMRI. So And it seems that now, every once in a while, we need to take into consideration the spiking, but a lot of it is that there's a lot of consensus that the main portion comes from the summation of postsynaptic potentials, not for all types of brain imaging, okay? Now, that if you have very high frequency recordings, then it becomes different because then you start to resolve, let's say, more of the spiking activity. Now, so I don't think it's a problem unique to EEG or MEG. It's one of the problems of doing in vivo measurements. No. Now, regarding what you were saying before, no. Okay, so the problem is that it's not dipole versus distributed sources. Now with machine learning techniques, you have the mixture of all of it. In fact, we in the early 90s introduced a form of solution which is the combination in statistical terms of a minimum norm solution, let us say a ridge regression, with the lasso, the L1 norm sparse solutions, and that could find either dipoles or distributed solutions.
Okay.
Now there is a problem that all of the inverse solutions depend on the assumptions you put in. The better knowledge you have, the better you get. If you have the guy's individual anatomy, then you can get much better results than if you're working, let's say, with a statistical template. But you can't get results with a statistical template.
Yes.
In fact, that was in '93 when Alan and Arthur and all those guys started to work on ICBM, the International Consortium for Brain Mapping. We hitched on immediately, and we became very good friends with Alan and with Keith Worsley, no?
Yes.
And we started using their statistical atlases to do inverse solution, and it improved incredibly with respect to just not having any information. But the other information that's important is the connectivity, because there's a problem, and I classify the inverse methods in generations according to whether you pose any sort of connectivity. And then I call this first generation methods. This is Arun Vareda, Loretta, because what you do is you say the sources are independent.
Yeah.
Then you do the inverse solution, and then you calculate the connectivity.
Okay.
What we've been working on currently is third generation methods where you have to estimate the connectivities too.
Yes.
And you can use as prior information.
That's cool.
What you have from DTI, and then let me tell you, this is a paper that we have it up in bioRxiv if anybody's interested. No, we've already submitted it to several journals because it took a lot of painstaking corroboration. And what we found is that you get orders of magnitude of increase in accuracy, both of connections and activation, if you estimate the connectivities.
Yeah.
And we checked this with this monkey ECOG. So what did we do? We said, okay, with 19 electrodes, just 19 electrodes, what is the method? How well do you predict connectivity on the ECOG?
Yeah.
Where you, of course, have to model physically the lead field for the ECOG and for the EEG, for both.
Yes.
And what we found is that the methods that have been so useful in multiomics and machine learning, the use of structured sparsity, a series of things, plus some common sense knowledge about how the brain is arranged, it increases things a lot.
Huh.
The way this is going to go, the way I think it's going to go, is that the more information we have in large databases about individual and statistical properties of the brain, the more prior information, because the essence of an inverse solution is that you're solving an inverse problem.
Yeah.
That has to have, an inverse problem is ill-determined. You need to put prior information.
Yes.
That prior information can be statistical, from a population if you don't, or it can be specific to an individual. Yeah. Let me tell you, we're in a cool project now. You just, jogged my mind. That is something that's being headed by Catherine Ammons and Alan Evans, and it's the Big Brain Project.
Yeah.
So what we've done, we're part of something called Work Package 5, and one of the things we've done is already using big brain anatomy, we're doing inverse solutions. And what we hope in the near future is that as information comes out about cytoarchitectonics, receptor topography, we're going to build that in
Right.
Because the other direction this has to go is that you just don't do an inverse solution. The inverse solution is the solution to the observation equation. What's important is the dynamical equation of neural interactions.
Yes.
And the modeling is going, it's a state space model. The engineers always separate these things. We've been talking about the observation equation and its inversion.
Let me ask a couple of questions here. So one, when you talk about connectivity, so, certainly now, even, in the context of doing like layer fMRI, people suggest, oh, well, gamma frequencies might be feed forward and lower frequencies might be feed back. And so is there a frequency dependence in terms also of looking at connectivity?
Yeah, it's definite. And in fact, when I was thinking about optically pumped, OPM, there's some cool papers now, precisely by Gareth Barnes, his group, where they have actually looked at layer-specific inverse solutions of MEG.
Yes,
okay?
I've seen that. Yeah.
It's really cool stuff. It really has us all excited, no?
Yes. Yeah.
But I think that a bit of what I'm saying is that the more information we bring in, like what you're saying, the type of connections, this idea, for example, this big brain project to try to align all of the different images, around and then this is prior information, and you can look at the posterior distribution after you've used the Bayes theorem to see how much actually depends on the data and how much you're guessing. When your posterior distribution is spread all over the place, that means that your priors are doing the job, not the data, not the information.
Right. No, that's cool. That's very cool. And also, and there's one other aspect that I think is potentially super profound. Potentially, is that I was recently talking to some people doing computational modeling, and the idea there is, there's this fundamental idea is that you might have these many different scales of networks in the brains, and even neuronal ensembles, they have, maybe our memories are stored as attractor states and attractors. And when you have attractors, you have oscillations, and it might be sort of a signature of, these attractor states sort of varying. I mean, the idea is, once again, trying to go from individual neurons communicating with each other to create this oscillation that sort of is a sign of an attractor state in some sense. I don't know.
I agree.
Okay.
No, I agree. And the problem here, you touched on the important thing, which is the crossing scales. Okay. The problem is that's one of the things that we discussed recently with Rainer Google with a number. We had a seminar. And what was one of the big problems? That we still don't have systematic ways of crossing scales.
Yep.
So, for example, the narrow mass models that we've worked with, and we've connected even at the brain level, they're very simplistic. It's just saying that there's postsynaptic potentials integrating. You have a threshold, which is a square thing. You have a distribution of thresholds. It becomes a sigmoid function. That's very primitive. A lot of what we're doing with there is the problem that was recognized, when there was neural network theory, and then people realized that it was actually a non-parametric estimation, and that the sigmoid function could be substituted by any other function, the REL function, what they call squashing functions. And what you were getting is non-parametric estimation. So that is a problem. Now, what I think, what we are working on now also is this problem of scales. We published a paper, a review in Human Brain Mapping a number of years ago, where we showed that some characteristics of joint EEG and fMRI recordings could be explained in terms of neural masses connected using realistic diffusion tensor imaging connectivity at the voxel level. This was 2009.
Yes.
But I think we have to have new generation neural mass models that are based on lower level simulations. These are the ideas we're working on now.
Yeah, I was also, one other idea. I figured might as well ask one. Something also that occurred to me a while I've been trying to think of is, it seems like a brute force approach, but as opposed to trying to do inverse modeling, is there any way of just creating a dictionary of, EEG patterns that are associated with bold activation patterns, and then just have this sort of lookup table of, try to make it a feed forward, a forward problem, but just have an extensive lookup table of EEG states with activation patterns.
Sure, you lose a bit of the biophysics there, but that's a powerful approach. That's why I say that though I like source analysis, and for example, I hate the term scalp connectivity because the electrodes in the EEG are not connected with anything but the amplifiers. No.
Yeah.
But that doesn't mean you can't look at correlations, which is different from brain connectivity. And you can look at the patterns of nonlinear association and do classification of states.
Yeah.
However, once you have a number of states that's large, then you're also solving an inverse problem.
Yep.
Because then the dictionaries are always overcomplete. In fact, there's a funny parallelism between methods that have been developed, let's say for time frequency analysis, for geophysics, and the EEG inverse problem. And they have different names, and people sometimes think they're different. But basically, it's always that you have, let's say, dipoles. That's a dictionary of a certain type that produces potential fields in the brain. ICA, that's another dictionary where there's been a reduction of dimensionality. But then many times it's overcomplete when you pool over, for example, Scott's, he has this huge dictionary of ICA patterns that are supervised. And then when you get all this sort of thing, you always have to solve an inverse problem. Now, the point is, do you want to put the biophysics of measurement? And then always, the test, the litmus test to know if you're solving a biophysical problem is if you're considering the measurement equation, the lead field. If you're not, it's pattern recognition, it's fine. It can be very useful. If you want to know something about where it's happening in the brain, then you have to put in the measurement process, the lead field, and then it becomes an EEG inverse problem. But they're all inverse problems because they're always overdetermined. You never have enough data for the amount of variables you're measuring.
That's a good point. That's a really good point. Just to deviate a little bit here. I mean, you've also been doing a lot of collaboration and just with a lot of other sort of modalities as well. And there's one paper that stood out. I just figure I might as well just highlight one of the papers. Or maybe two, but one is from Human Brain Mapping in 2019. This really interesting idea that crystallized and fluid intelligence is predicted by microstructure of specific white matter tracks. So you're basically looking at the fractional anisotropy in white matter tracks.
I love tracks.
That's fascinating, and I don't know if you want to mention it a little, talk about it a little bit, but the idea of that is that somehow. I'm assuming it's possibly correlated with anisotropy, where the more ordered the white matter tracks are, it correlates with higher intelligence.
It usually is. There's one exception that we couldn't find a good explanation for, but yes, it is. Here, the interesting thing was that this is what the editors, the reviewers and editors liked. First, it's in a population that's not the usual population. This is a population from Latin America and the Caribbean. This is something we've been doing, which is putting data from Cuba, Latin America, up in the public domain to increase the phenotypic and genotypic diversity. Second, there's been a lot of work done on intelligence and different measures of brain structure and activity. But unfortunately, I don't know why, but some decisions made by the big brain projects, they're cast in stone. So one of the things was that there wasn't a clear separation. And let's say, for example, some of the big projects in crystallized and fluid intelligence.
Yeah.
So the first thing we did, we used structural equation modeling. First, we identified that it was necessary to separate these two latent constructs, and then the latent constructs were put into, we looked at the relation with the different white matter tracks, and what we looked was at average fractional anisotropy across these tracks. Now, we did find very significant positive relations. There's one relation which is a bit difficult to interpret, but of course, this could be due to a confounding variable. The problem with determining causality is very difficult unless you're sure. So this was quite keen. It's part of something.
Yeah, everyone assumes that in white matter, the fractional entropy is sort of constant. It's sort of, enough to identify the white matter, and then they haven't looked at that. So that was interesting.
No. Well, you know that it's not exactly the same, and you have to look at the average. But you know that this better than I do. There's much better ideas about microstructure now than fractional anisotropy. This brings to mind something that I'd like to talk about, which is something that I really think of in the research domain, which is that we can't study each modality alone. We have to look at multimodal imaging.
Yes.
That's my interest in diffusion weighted imaging and fMRI and structural imaging. And the important thing here, I think, is that the way to link these could be empirically, which is fine, but it can also be model driven.
Yep.
And for me, that's very important.
Yeah.
Because if you have the model and then generate the forward models for each of the modalities, then you can have a principle. I mean, you need both. You need to see what associations there are, but you also have to do it that way. And we have a very cool paper, I found it, which is the one where in neuroimage, where we looked at surface area and white matter microstructure related to the alpha rhythm.
Yes, cortical thickness as well. Yeah.
And this one, why I find it interesting, because it starts with a very good friend of mine who had the idea, or has the idea, in one of the embodiments of his models. His name is Paul Nunes. He started neurophysics, I think. He was the guy that really, started neurophysics. We're great friends. But he had, one of his simple models is that the alpha rhythm is a standing wave, and therefore the cortical area should be proportional to the frequency, the peak frequency of the alpha rhythm, which is an interesting biomarker because it's highly heritable. It's very stable. It's the most stable of nearly all the biological, physiological psychology measures.
But it is modulatable, though. I mean, it is, it does, your eyes open, eyes closed, whatever. I mean,
yes, but once you have it in one state, let's say eyes closed, it is highly constant. It develops over age. It changes over age, but the pattern is highly heritable. It's very heritable. Now, it's the genetics determine it. Now, one of the things that we looked at in this paper with about 300 subjects that we did EEG. I mean, at the time we did that study, there weren't many EEG and large databases. So we had this database, which is small by today's standards, the Cuban human brain mapping data, which is now, by the way, publicly available through Nature Scientific Data. So anybody can go back and check what we did. The idea was that we had EEG, we had tractography, we had anatomy, we had some fMRI, but we concentrated. Okay, is there a relation between the surface volume and the surface area and the alpha peak? No, we didn't find it. Zero. Okay. But that doesn't mean it's not a good theory.
Yeah.
Because a good biophysical theory is falsifiable. And now, later, very soon after, Paul came up with a modification, but that's the way you go. You test that one.
Yep.
Now, but what we did find was, and here we were using methods to look at the correlation of the peak of the alpha with the white matter tracks. Okay. Using structured sparsity, machine learning methods.
Yes. And
we found that there was a correlation. So there was a significant regression.
A correlation between what and what? So alpha rhythm peak and
certain tracks, the fractional anisotropy. Here we did voxel by voxel in white matter.
Interesting.
So this sort of thing I think can be continued, but what was the idea? The idea here was to try to find the correlates of electrophysiology that are determined by structural imaging, other types of imaging. Let me give you an example of something that the neurophysiologists know. When you measure the latency of the somatosensory evoked potential, you measure the guy's arm or the girl's arm, you measure it because it takes longer. Yes. So you have to. So if you're going to measure brain activity, let's say using the EEG or fMRI, the structural and that's necessary to understand.
Yes.
And I think this is very useful.
In that paper, you suggested it was a cortical thalamocortical cycle in some sense, maybe that alpha waves
Yeah, because that is also another friend of ours. They have friendly arguments, which is Peter Robinson versus Paul. They discuss, is it a thalamocortical circuit or is it is it this global standing phenomenon? It could be both,
Yes.
But okay, we did this experiment. We say, okay, the evidence tends toward the thalamocortical circuit, the delay. Now, this also can be, this can be put into a model and falsified. But I think this is very important to try to pull together the different imaging modalities through models.
Yes.
It will also increase the explanatory variable. Because as in the example I told you about the somatosensory evoked potential, that is the length of the arm of the person you're measuring introduces a variability. That's a nuisance variable.
Yes.
When you get rid of the nuisance variable, then you can concentrate on the real things. And so I think that's how I can encapsulate the idea that multimodal modeling, subserved by modeling, could be a way to get rid of a lot of sources of. Now, the other point that we make in that paper is that we're not surprised that the alpha rhythm peak, I can tell you, we've measured this from age 5 to 97, and we've done it now again for 9 countries, the same story. The alpha peak increase is first, there isn't an alpha peak, there's a theta peak. It turns into alpha peak, it increases in height and in frequency, and in older age, it diminishes. It's like a regression. It diminishes in size and decreases. Now, what comes to mind with this? Many people have speculated. It's myelination.
Oh, that's interesting.
It could be other things. It could be receptor dance, whatever. But an important fact that seems to stand out and fits in with what we showed, it's myelination. It's speed of connections. It's what are the delays in circuits, reverberating circuits that produce oscillations. Now, if we don't measure this and if we don't know it, it's a source of unexplained variance that confuses the results.
Yeah. And it's mostly alpha that you measure just because it's the strongest signal. I mean, you can imagine this could be in other frequencies too, but maybe not.
Well, we look at all frequencies. The normative data we have is for all frequencies. There's a very popular model now, which Brad Wojtek has brought again to the forefront, which is that you have to separate this 1/f type activity from the peaks in the spectrum.
Oh, interesting.
And this is something that was already mentioned in the 70s by Sederberg. Actually, Roberto Pascual, while he was working with me in Cuba, we published papers on essentially the same model that's being now popular, and we looked at the development. Now, you have at least what we found at that time, we're confirming that, is that you have like an increase, a change in that. I don't like to call it 1/f activity. I think this is one of the problems where it comes with a connotation, and you can produce that type of activity with an autoregressive model of order 2, of order 1, I'm sorry.
Yeah.
So sometimes you can describe the same thing mathematically, but then some of the mathematical descriptions have more exciting connotations, but not necessarily they are an explanation.
Yeah.
So this decreasing activity, which we call the C process. This is a paper from the late 80s. And then you have peaks. And so there are different parts, and you can describe them, no?
Yeah.
Now, of course, this was looking at stationary segments, quasi-stationary segments. We have now time frequency analysis, and it becomes more complicated.
Yeah.
We're looking now at more interesting things like nonlinear couplings between frequencies and stuff. But yes, there are different parts to the EEG.
Yeah, and as you say, it's all kind of driven. I mean, in some sense, you're building this model. You're building a model from all trying to build the scales. You're trying to build the structure. You're trying to build the causality of what's what is generating these. And then also you put in age and cognition, and even you have a paper on phases of cognition, like mental mathematics and different frequencies. Yeah, it seems like there's just the very beginnings of this sort of model and being built, and maybe it will click in and it will all become clear at some point.
Okay, you got me excited about some things.
Well, let's shift gears a little bit. So you're in right now. You're actually in Chengdu, China. So you're not in Cuba, and you might want to, maybe if you wanted to talk a little bit about, why you're there and how long you're there, or if you're collaborating, and what is the, it looks like your work is the Cuba China Canada EEG consortium trying to do EEG harmonization.
Okay, very briefly. Okay, I started, we've been collaborating with Chinese labs since the 90s. Okay, in fact, the first quantitative EEG systems, the first digital EEG systems introduced into China were from Cuba. This was in the 90s, 89, 90.
Great.
So the thing is that, no, they now have a huge technological, they really leaped forward. But since 2011, I started collaborating with several groups here. And we came up with the idea that we could create a joint lab, which we call the China-Cuba lab, but it's actually an international lab. And that led to creating the Cuba China Canada project to try to promote multimodal databases that will be available through the Canadian Open Neuroscience platform to developing countries.
Okay.
And to look at health. This came out of a meeting that you probably remember perfectly well, that was carried out at the World Health Organization, which was, the brain projects meet the World Health Organization. I was one of the organizers. Carl Zils, Alan, a bunch of us were involved in that.
Yes.
And a bit what we identified is what were the gaps in the large brain projects that might, let's say, be impeding or slowing down that these brain projects have an impact on global health. So what we decided was to create this group. I decided to create this lab. I was traveling back and forth, let's say every 3 months, and this has slowed down due to the pandemic. Okay,
yeah.
And so actually, I still work with my lab daily in Cuba.
Okay,
and I work with people here. That's it's a bit of a stress.
Yeah.
And then from the CCC, but I think it's necessary, and also because the lab has students from Turkey, from Pakistan, and we have students from Africa. So it's become an international lab. And what we try to teach people is the basics of neurophysiology, of neuroscience, and how they can use different technologies to see when they work in their countries, if they can apply this to the problems we're concerned about.
Yes.
Actually, the CCC has then grown into something called the Global Brain Consortium. And there's a web page for that. You can look up Global Brain Consortium, where we have our main projects.
Yes.
We've had several meetings. And once again, it's this mandate that we have to look for ways to accelerate the introduction of the results of brain research into global public health.
Yeah.
Without ignoring the basic questions that have to be asked. So this is what I'm doing essentially here. It's fun,
Yeah. Is there any so right? I mean, there's 2 points there. It's like, right, one, in terms of how to make an impact on public health, and two, a lot of people with fMRI data, they're trying to do pooling of data and pulling out biomarkers. And is there any hope of certainly EEG data can be pooled? How are people using it, and are they extracting potential biomarkers that could be useful?
All over the place. You probably saw this paper in Science where you could do fingerprinting, identify somebody by a few seconds of EEG. It just came out recently.
Yes.
So there's more and more of this. And what's really needed are international initiatives that are as strong as for. Actually, the fMRI has led the way in federated data, open science. We need that same sort of thing.
Yes.
For EEG. One thing that's really crucial for EEG, and it's something that we're pushing in the GBC and the Global Brain Consortium. And in fact, Alan, who's with me as the co-PI of the Global Brain Consortium, just organized something in Canada called EEG Net. That is so the idea of EEG Net is something that Scott McKay, who's part of GBC, that Mike Milham, there's a bunch of us that are interested, is that we have to have data publicly available, and that EEG data has to be annotated by a bunch of experts so that then we can do some sort of real meaningful, let's say, extraction of biomarkers, deep learning, and so forth. Now,
so what do you mean by annotated as far as that's concerned? So is it sort of like labeled?
It's labeled. For example, what is the biggest problem and still in EEG? It's artifacts. I mean, it's a problem for any type of measurement, okay?
Yeah, but definitely.
But definitely, let's say you clench your teeth, and you're moving your eyes, and you're moving your head, you get artifacts. And this is one of the major problems. Now, this is a not totally solved problem. So, and in fact, there's a bunch of methods to try to eliminate them automatically, but at the end, they rely by visual inspection.
Right. Yep.
This is something you can't avoid, but if you're going to do something that's deployable, that you don't need a lot of technical expertise, you have to solve this problem to a greater degree. Now, how do you do that? The problem is that you put two GEG technicians who are certified, and they will come up with different annotations.
Yeah.
Different.
Yes.
And then another very interesting feature is that there's some things that are called grapho elements. Now, what are these grapho elements? They're sharp waves, they're things that have shape. They're squiggles in the EEG recording that mean things to people that have a lot of expertise.
Yes.
And but these also, there's ambiguity. It's like a fuzzy thing. So a public annotation of these EEG features coupled with the use of the modern methods for looking at biomarkers is going to be great.
Yeah.
There's a paper that just came out 2 days ago. I have it here with me, which it came out in Neurosalience, which is about trying to search for biomarkers unsupervised.
Yeah, right. That's exciting. I can imagine even you could have unsupervised, machine learning approaches that identify, annotate these signals and also pull out,
You should compare against something.
Right.
And second, you're not going to gain the trust of the clinical people if you don't show some level of congruence. The one I'm mentioning is by Dadi. It's called Population Modeling with Machine Learning Can Enhance Measures of Mental Health. Huh. This is a cool paper.
Yeah.
But that's the sort of thing, let's see, Danilo Stock is on there. Some of our other friends are there. And so I think that there's going to be, with artificial intelligence, a revolution in this whole thing. But it has to be grounded on gaining the trust, but also getting the experience of people who are in the field doing this.
Yes.
And of course, we came up with a model for sharing data, which was quite interesting. That's something we're doing now, which is doing a multinational normative data set. Okay. It has 9 countries. The idea was to share only very high-level descriptive statistics and anonymized metadata, not the raw data.
Okay.
Not the raw data. So what we did was to create, we've now finished this. It's on the webpage of the Global Brain Consortium. We've submitted for publication. It's 9 countries, about 13 or 14 sites, devices that are different. It's EEG, very simple, 19 electrodes, eyes closed. The people only share a summary statistic in the frequency domain, which is known as the cross spectrum. It is to say the cross spectrum and the spectrum for the 19 electrodes for a certain number of frequencies. That's the only thing they share. And then we use machine learning techniques to pick out the outliers. That allowed us to go back and say, hey, you guys have something wrong. And they say, oops, yes, we switched the order of the electrodes. That was really cool. That was really cool because it shows the direction and things where things are moving. We've confirmed much of the earlier work, but now the sample size is 1,700, which is much larger than the 300. I mean, not that much larger, and it's from 9 countries. And what we're doing, this is an experiment that people can share data. You know that there's always this, and a way of sharing data that overcomes some of the recent, let's say, qualms that people have about privacy, etc. No? And it's a cool project. We had fun with it, okay? But also we've caught up. We think that the whole deal of harmonization, that is to say, how sites that are different, and the people that put this into, let's say, the public consciousness are bioinformatics people with their batches of analysis.
Yes.
But then it's spilled over to MRI, to fMRI, to to the fusion weighted imaging, what we found is that there is a batch effect. Now, what we found by testing the classification of subjects is that you still get reasonable area under the ROC curve, discriminating, let's say, an independent sample of normal and controls. But if you do batch correction, the AUC goes up, the area under the ROC curve goes up dramatically.
Okay. So there still is a difference between, sites or vendors or, systems. Or
Exactly. And what we think we can do is get a dictionary of vendors or whatever, and then you're doing an independent study, then you say, okay, I have to do batch correction because that's what we did. We actually tested this using two nearby countries, which is Cuba and Barbados. It's the sample I told you about.
Yeah.
And what we use is, okay, they more or less both come from Africa, we use the same type of equipment, let's use the Cuban, let's say, harmonization data, to harmonize the data from Barbados. And it improved the classification. So we were right, because the equipment was very similar and everything. So what we think is that eventually, if there's cooperation, there will be, let's say, a dictionary or something, or you can even look to see which of the batch corrections you should use. And then there's a basic part, which is, let's say, the common structure, which is independent of batch. And that's what's being done with the harmonization. Yeah. And we have those curves, they look beautiful. They look really cool. We're doing this, by the way, using a Riemannian geometry representation of cross-spectral matrices.
Okay.
Because the cross-spectral matrices are covariance matrices in the Fourier domain. Therefore, they're not in Euclidean space. They're in a curved space. And what we do is that we take it to the tangent space of this manifold, and that's where we do all the statistics. It's really cool. I mean, mathematically also.
Yeah.
It's cool. It's cool.
That's cool. And it seems like, right. I mean, there's a lot of people working on it, but not, I feel like there's armies of people working on fMRI data, but it seems that it's still, I haven't heard about a lot of, this type of work with the EEG data, but it seems like you're saying it's growing rapidly, and which is great.
It's growing rapidly. And what you see is that there's more coordination in the fMRI world.
Right.
Okay. Somebody told me this, Paolo Rossini, the guy who was the president of the IFCN, of the International Federation of Clinical Neurophysiology, and we had a symposium recently. He's now running an EEG prediction of conversion to Alzheimer in Italy with a very large sample.
Wow. All right.
He's a clinical neurophysiologist, and he said, look, we have the disadvantage that when MRI came out, it boiled down to a few vendors, and it was easier to get them to agree.
Yeah.
In EEG, there are hundreds of different systems, and there's a lot of fragmentation. So part of the problem is subjective, part of that. And then, of course, there's not that many large databases as there are in the public domain that people. But now, Arno Wilringer, Mike Milham, ourselves, we've made public our data.
Okay.
In fact, I use that data, and I think that's the trend. I think people will catch on to this. Okay?
Yeah, or even having it seems so. It's ironic because EEG is one of the easiest things. I mean, it's relatively cheap, more cheap than, less expensive than MRI and PET and everything. And it seems like it would be great to have a multimodal data set where you can actually,
exactly
as well.
Exactly. And also where you could, because always I see this, that you use the EEG in certain circumstances as part of a system where you may be doing screening, and then you can end up using other techniques. You have to know how the EEG, or let's say the FNIRS, let's say less expensive techniques relate to the more, you have to calibrate them.
Yeah.
We did this in the 90s in Cuba when there was only one CAT scan, and we showed that we could detect the presence of something bad in the brain using EEG. And then you could use that as an additional criteria besides, because you never can get rid of the clinical opinion, to send people to get a CAT scan, let's say for a brain tumor.
Yes.
And so you see, if you have the different types of technology, you can use it at different levels to answer different questions with different levels of confidence. And there was a backlash in the US in the 70s when all these methods of quantitative EEG came out, because some of the vendors of the equipment started saying that this would do psychiatric diagnosis.
Yeah.
And that's absurd. There's no single technique that will do it.
That's exactly right. Yeah. It's always, for the sake of advertising and selling things, you oversell and then there's a backlash. But I think, right. I actually do feel there's a huge amount of potential. There's a huge amount of information in that signal, as you're saying, and we're still figuring it out. And it's exciting. Just to sort of, getting towards the end of this podcast, I just wanted to sort of talk a little bit about, in general, when I visited Cuba about 7 years ago with your workshop, I was impressed. I mean, you were mentioning as well the Cuban medical system, how it seems. I mean, it seems like it effectively, deals with. Like you're saying, they have the national screening, and there's things that are well organized and able to be nimble to respond to public health issues. I don't know if you wanted to talk a little bit about that, just to, your perspective of interacting with.
Sure, it's a unique experience. I think it's one of the unique experiences. There are probably others in the world where it's a poor country, a lower and middle income country, constrained by resources. But there's a public health system. And then what's been done is to match the work of the research institutes that go not only, you visited several of them, no? Where it's not only doing, advanced research, but it's also looking for solutions for primary health care.
Yes.
And but that requires, people tend to fly in different directions. That requires a political will of putting people together and getting them to learn to work together. Yeah. And it's not easy. Now, the problem is that some countries have public health, but then they haven't been forced to develop the technology, or they don't have the large research institutes. And there's some countries that have very good research, but they don't have good, a good public health.
Yes.
They have good high level health, but then when a tsunami like the COVID pandemic comes in, you see the gaps that you need to have. Public health also, you have the different levels. So I think our experience is interesting in terms of combining science, combining public health, and trying to prevent disease, because this is a mantra we repeat. It's easier, less expensive, and more effective to prevent disease than to cure it when it's in an advanced stage. That's the ideal. I think we've done quite well. An example now under tremendous stress has been the pandemic, which we were doing very well. The Delta variant got in and has created problems. Yeah. But our own, we have a problem which is still there, which is the trade embargo of the U.S. That's a problem. Yeah. So what happened? I have to say, first we developed our own vaccines. We have 10 vaccines, of which 3 or 4 are already. Some of them have been tested, let's say, in other countries like Iran. Yep. 92% efficacy. We're now in November, we should reach 90% of the population vaccinated without vaccine hesitancy, because in Cuba, doctors are not seen as people who are trying to get money out of people. They're seen as people who are doing a service. Yeah. There's a lot of public education about this, about the importance of science. And we were the first country to start vaccinating kids 5 years forward. Now, related, our center, we have 3D printers. I think you saw them, that we use for neuroscience.
Yeah.
We started producing ventilators for ICUs.
Oh, wow.
Okay? Because we couldn't buy them,
right,
because of the trade embargo. And our engineers went over the place and started installing our homegrown, which we obtained thanks to international solidarity, because the designs for 3D printers and everything was at open source. Yep. People would talk to each other. This was wonderful. This is how scientists, trying to solve people's problems, get together and solve it. I think that was wonderful.
Yeah.
We are doing a very interesting study, which is a longitudinal study of patients that had COVID and of, let's say, relatives that were suspected of having COVID but were proved PCR negative. It's going now. The second part of the study will be a year later. And the thing is that we have found the situation with long COVID and what I call brain-induced brain disorders. That's a term we just wrote for the National Science Review. This is a large National Science Review is the Chinese mainstream, let's say, equivalent of Science or Nature. It has 17 impact factors. So Alan Evans, Mitchell Valdez, my twin, a guy called Moomin Poo, who you may not know, he's very famous in monkey work, and myself, we published a paper which is an international call for research on COVID-induced brain disorders. And the point we're making is that there's so many people with this disease, and it's such a complicated entanglement, social, psychological, and perhaps brain-induced problems that to deal with this in a public health fashion, and brain research has to face up to the challenge.
No, it seems like there's a huge amount of work to be done.
This is an example that what we did was in this call to action is that we just reminded people of the same points we discussed at the World Health Organization. It is, if you have a large burden of disease, of people that are in underserved situations, and they're not only in lower middle income countries. I mean, we've talked about how the First Nations in Canada or the poorer people in this happens everywhere. They're underserved people. You have to have ways of reaching out to them to do preventive medicine. And this problem of COVID-induced brain disorders, it's really alarming if you look at the statistics.
Really?
There have been studies of electronic records. There are reports of 23% of people that report things. There's this UK Biobank study, and it's alarming, but it's a difficult problem. How? Because for heart disease, which is also a consequence, for any other disease, you have simple measures that can guide you. Yep. But for the brain, we always have the problem that you have the psychological tests, and the cognitive, but that's not enough.
Yeah.
Okay. So I'm sorry if I gave you this, let's say this thing, but you just touched the button on what I think is necessary. I think that people have to step up together, the researchers, and address this problem, because in this whole situation of COVID, it's a large part of the world that's still not getting either the vaccines or the attention, and this is it's an urgent problem. I think that the same as we're concerned with climate change, which is logical, we have to be concerned about the amount of people that are not getting treatment of any sort or diagnosis or anything.
Yeah, and the big problem also, is long COVID, and also the long-term effects after you get, it's a scary thing, and how people don't fully recover, and to try to quantify that in some way. It's just, in the past I always thought, I got a flu and I'm better and everything's fine, but it seems like with COVID there's some damage, and it's variable. It's all over the place. And you're right, having brain-based measures or good behavioral tests or something that can get a handle on this seems like a big task, but fundamental in that regard. One other quick thing, and so just before the very end, so I'm sure that speaking of sort of public health, or not really public health, but sort of issues and having to do with Cuba, and I just remember listening to a podcast, and I heard that your brother, Mitchell, was sort of chiming in on this whole thing with the sonic attacks on the embassies and things like that. And I figured might as well, since I have you on, have you chime in on your opinion about this, because I've actually lost track of what finally was concluded. I haven't been keeping up, but I'm curious as to your relationship. I don't even know if it's true if Mitchell was part of the investigation or what. But
no, Mitchell headed the committee of the Academy of Sciences. I was part of it too. We actually traveled at one point to Washington to talk with the State Department. And there's been full cooperation from the Cuban part. This is not well known, but there was cooperation between the Cuban police and the FBI. There's been a lot of, because we're as worried about this as possible. First, I have to say that I object to the term Havana syndrome. It's like saying the Spanish flu which originated in France, maybe.
Right. Right.
It's or talking about the Indian variant. Now it's called the Delta variant. So this syndrome where people have a very large variety. There hasn't been the identification of what is known as a syndrome in medicine, because it's a great diversity of things.
Yes.
We have been a bit frustrated because this immediately has taken on, let's say, instead of being a health problem that has to be solved, it's taken on a political connotation.
Yeah.
And what worries us is that there's no real explanation. We found very flimsy some of the attempts and reports that have been published, which, by the way, it happened in Cuba, and we haven't been invited at all to share data, to analyze. We even had a symposium in Cuba to which many of our joint friends went, which we made public, and where we invited people that thought there was an enemy weapon to be there, because we think that if there is an enemy weapon, it should be discovered, but we don't see much evidence for it. We think, that the problem with this is, as many things in the world have become in recent years very politicized, and it's become very divisive, And I think that there's some things that can't be solved that way. You have to solve them rationally, with a cool mind, exchanging ideas, hearing other opinions, looking at evidence. Well, when we did the symposium in Havana, there were people that came up, and there was some recordings of the sonic attacks that some people, not all, said, and there were some scientists from Jamaica saying that it was a cricket.
Yeah.
And when there's doubt, you have to weed out, because if not, it'll become a mystery. And now, unfortunately, this seems to be something that is being claimed all over the world. It's happening in, let's say, it's happening in Colombia. It happened supposedly in Austria and in other parts. So it's becoming alarming. But we think that the only way to get at the end, by the way, many eminent scientists from the U.S. There's one guy who headed research in the Navy for weapons that could be used by ultrasound, and he's part of our panels because we're not political. We just want to know what happened,
right? And
he says that it's extremely unlikely, but much of this work has been done behind closed doors. There's always the suspicion that there's a foreign agent. When you think it's a foreign agent, then it's more difficult to find the truth. And what I'm worried about is that there are people who are suffering. And for example, many of these might have a problem that is in the brain,
right,
but is caused by several factors, and not. This is what is known as a neurological functional syndrome.
Yes,
and there's a lot of literature on it, and it may not be that, but if people that do have that are not correctly diagnosed, the first treatment is to have a correct diagnosis.
Yes.
And I don't think there's clarity of this. And I think that what has impeded clarity has been the politicization. People, one party trying to, in the US especially, trying to gain points over the other one. Cuba was accused at one point. I mean, that fell apart. We don't have the technology nor the interest, okay, for doing anything. I mean, that's the most absurd. After Obama opened up and we had the possibility of normal relations, which I remember at my center, it was broadcast when Obama and Raul Castro mentioned it, and we erupted in applause.
Yeah.
For us, relations with the States is essential and great. Now, so what I'm saying is that I feel that it's not well studied. There isn't a diagnosis.
Yep.
It's being used politically. The name is incorrect. Okay? It is newsworthy because, of course, this sounds, like something really, the aliens are invading or something.
I mean, that's part of the problem, right? It's so
the people are suffering. The people are suffering. They have a right to demand treatment, but what they need to have is a correct diagnosis and getting to the bottom of this. Okay, and you can look up. We have a report of the Cuban Academy of Sciences, which anybody can access, where we say what our doubts are. I mean, why we think that things are not clear.
Yes.
Okay.
Yeah.
Yeah. Well, also, what I object to is any form of impeding scientific exchange for any reason. Well, you know that. I mean, nobody should do that. In fact, we have very good examples where at one point, due to the embargo about 4 years ago, suddenly in Cuba, we couldn't access PubMed. And we spoke to government officials in the US, and that was solved.
Yes.
Because many of these problems, if if people look at it rationally, I mean, there's no point to some of these things.
Right. Yeah, no, I completely 100% agree with you. I think that's, and it's tricky. I mean, you have a landscape of ideas, and the only way that the best ones can thrive is if you have this free exchange, and sort of. But it's very delicate. It's very delicate because then you have bias, you have agendas, you have many things happening, and yeah, I mean, in science you have disagreements and arguments, but it's usually worked out in the data. You eventually the truth comes through because you care about the data.
People can reanalyze the data. They can look at it. They can discuss. The Canadians, by the way, consider that this could have been excess of anti-mosquito agents.
Oh, that's interesting.
They came with that theory too, and they're actually doing a joint research with it. They proposed that theory. They said this could be organophosphates, which could have been done by extra, because mosquitoes are a problem. And but you have to test that.
Yeah.
I mean, there are alternative hypotheses. Maybe that's not true. Maybe the other's not true. But you're not going to get at the truth if you start doing things behind closed doors.
I agree 100%. So, okay, well, thank you. And also let's just to wrap it up, is there anything, I mean, there's so much more that we could have talked about, like, for instance, starting LabMan, like, the local chapter for OHBM in Latin America and neuroscience in Latin America. But these are all things that maybe we'll talk about another time. But is there anything that you'd like to add? Or, I mean, it's been a wonderful
Not much, really, because essentially one of the things that worries me, I just want to say, is that the pandemic has put the world back a lot. It's dropped the economy, and there's been a trend that there's a growing inequity in the world. I mean, this is obvious, no? So the general level of people, because some countries have pulled their people out of poverty, China, other countries. So the general level of poverty is less in the world, but the inequity has been growing. Now, this inequity is also reflected in science. And the pandemic has put a strain on economies and things. So one last thing is that more than ever, the universal spirit of scientists, the humanitarian spirit, the exchange is important. That's what I think is the most important thing. And that we have to think of those people that are less fortunate than us and try to see how we can help them in every way by being more inclusive, by helping them develop science. That's a bit what I wanted to end with. Okay, I started my work under that flag with the people that came to Cuba to help us develop science where there was nothing.
Yes.
And then I feel that those countries that have developed science, they really should have the moral obligation to help other countries that are less fortunate. And it's a very difficult thing because you have. Sometimes science is not prioritized in the country by the own political elite. And there's no way to drive it. There's not funding. People try to go back to their countries and then sometimes get very disappointed because they can't do work and they end up by being part of the brain drain. These are problems that should be continuously talked about. They don't have an easy solution. We can't hope to solve all the problems, but at least knowing about them and trying to help is important. That's the last thing I want to do.
And it seems that trying to spread the science and spread the impact is, it's tricky because there's multifaceted solutions. There's potentially political solutions, but you're right. The principle of using science, using technology, using that philosophy of and also the science benefits from the spread as well. And I think, one hopes that it doesn't lose any foothold and try to keep on making progress. One hopes that happens, but there's other forces. But I'm still optimistic. Even though you're right, things have taken taken a little bit of a hit with COVID.
Well, I mean, we have a lot to do with physics. I'm just mentioning the boundary conditions. Within the boundary conditions, there's a lot we can do. So
Yes.
there's no excuse of giving up because of the boundary conditions.
Yeah, exactly. Exactly. All right. On that note, but I'd just like to thank you very much for coming. This has been an amazing conversation, and I really enjoyed it. And and I wish you the best.
Okay. Well, I hope we see each other soon.
Yes.
Maybe in SPM. I hope travel eases up and that we're able to see each other.
Yeah, hopefully in Scotland or where the next OHBM is or whatever. So, or some workshop. I'm sure that will, before we know it, it will start up again. So, and be regular. Let's hope so. All right. Thank you.
Thanks. Okay.
Thanks.
Neurosalience is brought to you by the Organization for Human Brain Mapping. This week's episode was produced by Rachel Stickland and Anastasia Brovkin.